As you all know, everyone, that last week we did begin with rate and extent of reaction, and this week we're going to continue having a look at rate and extent of reaction. We're going to finish it this week before we move on to chemical equilibrium, which is the next section. Okay, so chemical equilibrium forms another subsection of the section or topic or unit chemical change. So just a bit of recap from last week. We went through a bit of revision, looked at a bunch of definitions such as bond energy and endo and exothermic processes. Okay, we took down a lot of theory, went over some enthalpy, went over what activation energy was. We looked at potential energy diagrams, right, which were drawn. And we looked at the introduction to rate and extent of reaction, what is meant by rate of reaction. We looked at collision theory. We did go through frequency of collisions, and we went through energy of particles, and we also went through correct orientation. Now, to begin with this week, we're going to have a look at factors that affect the rate of reaction or the reaction rate. Okay, and there are 5. Okay, 1 being the nature of the reactants, the temperature, concentration, reaction surface area of a solid, and the use of a catalyst. Okay, which by far number 5 we should be familiar with regards to last year when we did this in grade 11. We know what a catalyst, well, we should all still remember what a catalyst does and the part that it plays when it comes to rate of reactions. Looking at the first one briefly, the nature of reactant or the nature of the reactants is that some chemical compounds are in fact more reactive than others. Okay, that is true. Okay, I know this because the reactivity of the alkali metals increases as we go down the group on the periodic table. Okay, we obviously know the different groups. We have alkali and earth metals, we have different metals, we have the halogens, all those different groups that we find on the periodic table. Okay, so the reactivity, alright, or the rate at which the reactants would react as you go down the group of alkali metals in the periodic table, they do increase as we move down that column or the group. Okay. Another example is if we take the example of potassium and sodium. They are more reactive than heavier metals. Alright. So potassium and sodium are more reactive than heavy metals such as, or heavier metals rather, such as zinc and copper. The strength of the bonds that are between the particles and the activation energy required to break the bonds does influence the rate of the chemical reaction. So 2 things, okay, which is the strength of the bonds. Alright, remember from grade 11 we learned hydrogen bonds, we learned polar covalent, all those different types of bonds that are present. Okay, so the strength of the bond and the activation energy or the energy that is required to break up those bonds, alright, that will influence your chemical reaction. Therefore, the simple particles, such as atoms or ions in the solution, they will react faster than more complex molecules. The next one is temperature. Okay, now we're basing this temperature according to collision theory. Okay, now according to collision theory, if the temperature of a reaction mixture is increased, okay, what is going to happen? Okay, the speed of the average kinetic energy or the speed of the average EK of the particles, they do increase. Okay, basic. Okay, that means we'll have more particles that have more kinetic energy, alright, that is more, either more than or equal to the activation energy. Alright, and we know what activation energy is, right? The energy that would be required to break the bonds. Okay? As a result, there will be more collisions and also more effective collisions. Okay, we already went through effective collisions previously under collision theory. Okay, so this is sort of like a recap. Okay, there'll be more collisions and also more effective collisions per unit time. Okay, so in other words, effective collision, again, when those two particles collide, there will be a reaction that takes place. Alright, which leads me to my next point. Therefore, the rate of reaction will thus increase, and low temperatures lead to a decrease in the reaction rate. Okay, so if temperature is increased, it's a good thing. Low temperatures do lead to a decrease in the reaction rate. So if you want to slow down the reaction rate process, one of those factors would be to just lower the temperature. Okay, for example, if you lower the temperature in your refrigerator, okay, if you lower the temperature in your refrigerator, that does mean that you slow down the rate at which your food starts to decay. So you slow down that decaying process, right? If you lower your temperature fridge, you increase the temperature of your refrigerator. Obviously, it becomes, in quotation, warmer, right? Warmer. In other words, minus 18 degrees Celsius is warmer than minus 20. Minus 20 is colder. Okay, so if you increase your, okay, I think the temperatures that I have on my refrigerator, I got minus 16, minus 18, minus 20, and then I think I got minus 20 something. I don't know what else is on there. Okay, I usually like to leave it on minus 20 or minus 18 between those two because that's relatively cold. Alright, slows down the rate at which my food will start to turn funny colors. Following on from temperature is also concentration, and we also look at this according to collision theory, ladies and gentlemen. Alright, now if we increase the concentration, alright, of a solution, alright, again, or if we increase the pressure of a gas, alright, you increase the pressure of a gas by decreasing the volume, alright, of the surface area. Okay, this will also increase the rate of the chemical reaction. Okay, but if we, with an increase in reactant concentration, if we increase the concentration of a certain reactant, okay, that means that we have more particles per unit volume in the container. Okay, remember we measure concentration by the number of moles of a substance divided by the volume of that substance. Okay, that will determine our concentration. Okay, for example, R.o.R has quite a high concentration. That's why we always refer to R.o.R as being concentrated. So what we have to do is we have to obviously throw more water to dilute the concentration of the R.o.R. Okay, so obviously make it taste obviously not as sweet. So with an increase in the reactant concentration, there are more particles per unit volume in the container, of course, which is exactly like, for example, the R.o.R example I just used. What happens is that the particles will therefore collide more frequently. Again, the third point there, which is similar to the one in temperature, there will be more effective collisions per unit time, and thus the rate of the reaction will increase. The reaction surface area of a solid. Now, when a solid is divided more finely, so in other words, if you take a solid and you crush it up nice and fine, right, and you obviously convert it to powder form, the reaction surface is much greater than in a more compact form. Okay. When I do that, all right, after I've crushed it into powder, the surface area is much greater than in the more compact form. Now, according to the collision theory, there is a greater surface area for collisions to occur. When there's greater surface area for more collisions to occur or take place, there are more effective collisions per unit time. Right? Thus, the rate of reaction does increase. If we take the example of Panado versus Grandpa, okay, we all know Grandpa headache powder is powder, right? You don't get tablets, you get it in powder form. That's why they say usually, or a handful of people say this, that grandpa works better than Panado, because Panado is still in a tablet form, for example. We're ignoring Panado syrup for now. We're talking just taking Panado tablets versus grandpa powder. They say grandpa does get to work a bit quicker, all right, because there's the total surface area of the pieces is greater than in the compact form, so it does get to work faster. Alright, it brings relief much faster than in a tablet form, because the body, alright, a little bit of bio here, the body doesn't need to break down the tablet itself. It's already broken down in grandpa form, so it just goes straight to work immediately. A catalyst. Okay, should all be familiar with this one. Okay, now we know what a catalyst is. Just a reminder, a catalyst is a substance that affects the rate of a chemical reaction without undergoing any permanent change or being used up in the reaction. Okay, we also know, just recapping off the top of my head, that a catalyst can be a solid, liquid, or gas. Okay, it can be a solid, liquid, or gas. Common catalysts or common catalysts, not sure which is the plural, which is the correct one. Okay, but common ones that are used that we've seen before is H2SO4, which is sulfuric acid. We know that does speed up quite a few reactions that we have seen over the years of us doing physics and chemistry. So sulfuric acid is quite a common catalyst that is used. Okay. Another thing off the top of our head quickly, we know that a catalyst that speeds up a chemical reaction, okay, is known as a positive catalyst, okay, and that's the most common one that we all deal with, or that we have dealt with, okay. A catalyst that speeds up the reaction, in other words, that would lower, of course, the activation energy. And then we have also a substance that slows down a reaction. Alright, in other words, a substance that makes it more difficult for product to be produced. Alright, that is called an inhibitor. Alright, INHIBITOR, inhibitor. Okay, but according to collision theory, how does a catalyst work? Alright, it lowers the activation energy, as I've mentioned. That means more particles have more kinetic energy, so more energy to boost and collide. There's a great chance, therefore, of effective collisions, and as a result, there are more collisions that occur per unit time and thus increase the rate of reaction or the reaction rate. Right, so over here we have some basic questions. Okay, this is just basic questions getting us involved in the section of reaction rate and rate of reaction. Okay, so a couple of definition questions there quickly, which is just define enthalpy and the heat of reaction, activation energy, endothermic reaction, and just asking us to define a couple more things. Just check if that is the only questions that are present there. See if there's some. Yeah, okay, that is the only 3 questions there. All right, so let's give this a bit of a cracker. The reaction rate graphs. Okay, so with reaction rate graphs, these are I wouldn't say very different from your potential energy. They are different, okay, but they both have one thing in common, and that is we are still showing the reaction. That's what we're still graphing, okay, except that when it comes to reaction rate graphs, we're not drawing potential energy graphs. Now we're obviously drawing a graph of mass or volume increase of a product or of a reactant versus time, of course. So if we draw a basic reaction rate graph, okay, so I'm going to get my normal clear color going here. Okay, here we go. Okay, so over here, what we're going to do, we're going to be measuring, let's take for example, the mass, okay, in grams per volume of a product formed. Okay, so I'm still writing it alongside here. I'm going to write mass, which is grams per volume, alright, which is going to be measured in centimeters cubed, okay, of a product formed. Okay, and of time, and on the x-axis you got time. Okay, so we're actually graphing, okay, the product. Okay, so how that would obviously look. Okay, if we got two time intervals, it looks like a curve that starts like this and then plateaus, right, into more or less a straight line. Okay, I'm just going to extend the bottom line over here. There we go. Okay, so that's how a reaction rate graph would look. Okay, so let's say, for example, here's my first time interval at this point here. So I'm going to just try and draw it in a straight, sorry, I messed that one up, line as possible. I have to go very slowly. There we go. So we got a time interval over there, which I'm just going to denote as t. Okay. Now, a factor that is always controlled. Remember, when we're graphing anything, we're obviously looking at two variables here. Okay, we're obviously looking at independent and dependent variables. Okay, so the independent variable in this case, all right, will obviously vary in different graphs. Okay, your independent variables can sometimes either be your temperature, it can either be your concentration. All right, that your independent variable is your variable that is obviously controlled. Okay, what is the independent variable of this graph? Time. Time is your independent variable here of this graph. Okay, that is the factor that is controlled. Okay, your mass per volume of the product that is formed, that is your independent variable. That is your dependent variable. Sorry, we already established the independent was time. So always when you're looking at a graph, just a tip, if they ask you, when they give you any graph, and I struggled with this in the first year of doing physics, that was in grade 10. Okay, I got it right in grade 11 and 12, is that when you are looking at a graph of anything, okay, and you see, and they ask you to, from the graph, determine the independent or determine the dependent variable. Your independent variable is always on your x-axis, okay, and your dependent variable is always on your y-axis. There we go. Next. Cool. So time, and okay, so let's say, for example, this is our first reaction. Okay, this is our first reaction. Okay, and then all of a sudden we get another reaction. Okay, dotted lines. Okay, there we go. Okay, this reaction occurs over here. Okay, we've got another T. Okay, so we can obviously see that T2, this is T1 and T2, okay, we can obviously see that there has been two different reactions. Okay, this is the second one and this is the first one. Alright, you can see that there are different reactions, okay, but there's no further increase in the product. Okay, we can see that the gradient of the first one is gradual or less steep compared to the second graph. Okay, we can see that, right? Okay, we can definitely see that. So we got a steeper gradient here than that of the first one. Okay, so it's important to know that maybe that I've lowered this reaction that has recurred in another time interval, that possibly this could have been the result of using a catalyst. Alright? So this is how I've graphed two different reactions, and this is probably how they'll give it to you in the exam and ask you questions based on a reaction rate graph like this. Okay, so a heading, of course you need a heading for your graph. So this is a mass per volume increase, brackets of product, versus time. Okay, it's a mark. Okay, it's a mark for your heading, it's a mark for your labels, etc., etc. Now the Maxwell-Boltzmann distribution curve. Okay, to begin, so in a gas mixture, molecules move, obviously they move constantly. Alright, they're free to roam, free to just go about the day, admire the view, have fun, blah blah blah. However, at a specific temperature, the kinetic energy of some of those molecules will obviously differ from others. Alright, some will have more, some might have less. Alright, two people, Maxwell and Boltzmann. Alright, so this wasn't one person, this was comprised of two people. Alright, they developed a distribution curve of the kinetic energy of the molecule, alright, or molecules versus the number of molecules for a given gas sample at a specific temperature. Okay, let's read that again. So these two people, Maxwell and Boltzmann, two scientists, they decided to develop a distribution curve of the kinetic energy of the molecule, alright, versus the number of molecules for a given gas sample at a specific temperature. Okay, so they are measuring, alright, the kinetic energy of molecules against the number of particles or molecules with a given kinetic energy. Okay, so your independent variable in this case would be the kinetic energy of the molecules, and your dependent would be obviously on the number of molecules with a given kinetic energy. Alright, so let's go see how a Maxwell-Boltzmann distribution curve would look like. Alright, so again, I have my, okay, I meant to draw it in white, but I'm just going to leave it in red. Okay, so over here on my y-axis, I got my number of particles with a given EK, or given kinetic energy. I'm just going to write EK. And on my x-axis over here, I have the EK of molecules, which is the kinetic energy of molecules. Okay, over here, obviously 0, and to represent it in another color, okay, my distribution curve is going to look somewhat like this. Just get a sturdy hand quickly. Okay, good. And over here, this is T1 up top here. Use another color. T1 over here, and over here, just when this graph decides to plateau out, okay, you have your amount of EA, or your activation energy, and over here in this section, this is where your particles, okay, with your EK or kinetic energy, which is greater than or equal to your activation energy. Okay, that is your typical depiction of a Maxwell-Boltzmann distribution curve. Okay, I will come back to this. I just want to give a note about this curve quickly, and then I will come back to it. The curve goes through the origin where EK is equal to 0, in other words, where there is no kinetic energy. Okay, the area that is underneath the graph is equal to the total number of particles that are in the system. Okay? Notice that again the curve does not touch the x-axis. Alright? Why? Because this is where your small fraction of particles that have a higher kinetic energy than others. Okay? This is what that introduction was explaining. Okay? Your peak in your Maxwell-Boltzmann curve will indicate to you where that is probably where the particles or the particles in the system have the most kinetic energy, will be obviously at your peak, of course. That is your normal standard. Alright, now let's go back to it. Maxwell-Boltzmann distribution curve. Alright, obviously it's my heading as well. Is it two? No, it's two N's. Boltzmann. This is not the only curve that does exist. Okay, of course we have the presence of an increase in temperature, an increase of course in concentration, as well as the increase in the use of a catalyst. So the next question would be like, how would a Boltzmann distribution curve look when we increase the temperature? Okay, I'm sure we all have this curve down. So how would a curve look with an increase in temperature? Okay, so I'm going to draw this graph just a little smaller compared to the other two graphs that I've drawn. Okay, so this is the increase in temperature for a Maxwell-Boltzmann distribution curve. Increase in T. Okay, so for example, from T1 to T2. Cool. Again, we have the EK, or kinetic energy of particles or of molecules. Okay, and here we have the number of particles or fraction of particles with given EK, whichever one you would like to obviously use. Okay, I'm going to use fraction for this one. Fraction of particles or molecules with given EK. Kinetic energy. Right, cool. So if we have our original one, okay, of course we have 0. So our original one going up like that. Okay, that's our original. Okay, this is at T1. Now if we increase the temperature to T2, okay, how's that curve going to look? Curve's going to look a little more spaced out. Right, it's going to look a little more spaced out. Alright, this is at T2. Okay, so if I just extend my line of the first one, just a little bit over there, okay, so I can see definitely at the bottom over here, this is where the activation energy would obviously be. So let me just fix this graph a little bit. I don't like the way I've drawn it. I've drawn it too far down. Okay, I'm going to increase this line over here. That's going to stay there. The red line is supposed to be just above it. There we go. So this is the part over here where the activation energy is obviously present. Just at about here. That's your EA. Okay, this is normally shaded in, right? This normally shaded in part. Okay, we can definitely see here that T2 is greater than T1. What happened is that the peak is wider and to the right because more particles have a higher kinetic energy. Okay, so we see that more particles here do have a higher EK due to an increase in temperature. Okay, and therefore in this case over here, this little shaded area that we see over here more particles have a kinetic energy that is either greater than or equal to the activation energy. Okay. That's what happens when you, to the Maxwell distribution curve, when you see an increase in temperature. Okay. A similar thing does occur with the increase in concentration. Okay. If the concentration of liquids, all right, or solutions, is increased from C1 to C2, all right, or the pressure of a gas is increased by reducing the volume, then that means there is more particles per unit volume, and the concentration would obviously increase. So again, I got my little graph here. Okay, I've got my EK, alright, that I'm measuring here, and again I got my number of particles. Okay, I'm going to shorten it quickly just to save time. Number of particles with given EK. Okay, I got the kinetic energy of the particles, which is known, we'll measure that in kilojoules. Alright, and I have 0. So I start out, there we go. I have my C1, I have my C, but I'm actually going to leave that as, let's change color quickly. There we go. That's what I want. Okay, so let's say the purple was my C1. That was the reaction or the curve at the first concentration. If I increase the concentration to C2, okay, well, first of all, we can see that the peak is definitely higher. Okay, the peak is over here for C1, but the peak is over there at C2. Okay, the area under the curve is greater, obviously, for C2 than it is for C1. Obviously, it covers more area. Okay, and that obviously means there are more particles per unit volume in a container. Alright, and we can see here that at C2, alright, C2 is obviously greater than C1, we can see that more particles have a kinetic energy that is greater than or equal to the activation energy. Alright, more particles. Alright, and we can definitely see also at C2, okay, that the peak is also higher. Okay, it's also worth denoting here on the note section. Yeah, more particles per unit volume. Therefore, more particles per unit volume per unit volume. Alright. Okay, and this was the graph heading, of course, increase in concentration. Okay, do we all have that? There's one more graph to draw, and then we are done. So the curve for a function of a catalyst, which is the final one. Okay, so we obviously know how a potential energy graph would look if we had to insert a catalyst in the reaction. Right? We obviously know how that curve would look. That would obviously lower the activation energy on a potential energy diagram. Okay, if a reaction had been catalyzed. Okay. So the same thing occurs on a Boltzmann distribution curve, all right, under the function of a catalyst. Okay, so but what happens is that we don't draw a separate curve for the function of a catalyst. Okay, so what happens is that if we have our curve over here, let's say for instance, this is the presence of the initial activation energy without a catalyst. Okay, that's how that little shaded area is there. If we add a catalyst to the reaction, how it will look and how you would indicate it on the Maxwell-Boltzmann distribution curve is the activation energy just moves lower. You indicate it over here, and you would call it EA, and in brackets you would denote it as CAT for catalyst. Okay, so I have lowered the activation energy, or we can definitely say that I've shown that the activation energy has been lowered, alright, in the reaction, but the distribution curve has not shifted. Only the activation energy is lower. Alright, so let me just add that as a note for everybody. So the curve, alright, not shifted, and it will never shift even if you use a catalyst. It will never shift. It's not shifted. Okay, only the activation energy has been lowered. Okay, what does this mean? Okay, that the particles, they need less energy or less EK to react. Okay, and finally there are now more particles. Again, there are more particles with kinetic energy, or with a kinetic energy that is greater than or equal to your activation energy. Thus, due to the function of a catalyst being added. And that actually concludes the section of rate and extent of reaction. It concludes the section. Okay, following on from this section is chemical equilibrium. It's a little bit more intense, and or should I say quite intense, but this concludes rate and extent of reaction. I thank you.